Hey guys! Today we are starting a new topic and we're going to talk about organic chemistry. And just to quickly give you some background, so organic chemistry is a whole subject in college. I mean, you could take it for a year. I did take it for a year. And, it has a reputation. But I think it's a really cool class, and what's crazy about it is you spend a whole year learning about one single element, and that element is carbon. And before going into the class, I was like amazed that you could spend so much time learning about just one element. Well, carbon is really important to us because it is the backbone of our life. We're all made out of carbon, and it just is everywhere. It's a very important element. So without carbon, I mean, our DNA has like a carbon chain backbone. We wouldn't exist. So it makes sense that you could actually spend a whole year talking about it. We're only gonna spend a week and a half talking about it, but hopefully it'll give you like a nice brief introduction to what it's about. So let's get right into it. So why carbon? Carbon is the selected element that's like premiered on your periodic table, on your reference table. And that's because, like I just said, life is largely based off of carbon. We have 10 million known compounds, 9 million of which are organic. When you say it's organic, I don't mean it in terms of like the grocery store definition of organic. It doesn't mean it was like made without pesticides. Organic in chemistry land means that it has carbon in it. So if you say, oh, that's an organic compound, you're saying that that compound is mostly carbon. And so like when you look outside your window, you're looking at a lot of carbon stuff, like the grass, that's all made out of carbon, the trees, that's carbon. So like life is largely carbon, which is why when you burn fossil fuels, like petroleum, for example, this is all from decaying trees and plant matter. So it's all from carbon. You're burning carbon, which is why you're releasing carbon dioxide into the air, is because you're burning trees, which were made out of carbon. So, the carbon cycle and all things carbon are very important. We're made out of carbon, our DNA, proteins, carbohydrates, lipids, it's all carbon. I mean, there's also other elements. Hydrogen is in there a lot too, but like carbon's a key factor. So, this is just like a quick picture of the carbon cycle and how it, you've probably seen this before in earth science or bio. So here I have a picture of butter, and this is the molecular structure of what butter is. You have glycerol and fatty acids coming off of it, and so this is an organic compound. Fats are usually largely made out of carbon and hydrogen and oxygen. So notice how like the carbon is the main kind of backbone, what's like holding the whole thing together, and then stuff's just bonded off of it. So we're gonna take a minute to just talk about some of the properties of organic compounds. Are they usually soluble in water? What are their melting points and boiling points like? And is it an electrolyte? And while like carbon compounds can look completely different, like you can have a tree that's mostly carbon, and you could have a person, and you could have butter. I generally, when I want you to think of organic compounds, I want you to think about butter for the most part. So let's go into it. Some characteristics of organic compounds. Usually they're called hydrocarbons. The reason why organic compounds are called hydrocarbons is not because there's water attached to a carbon. That is a common misconception. There is no water. It's called a hydrocarbon because you have hydrogen attached to carbon. So I know there's oxygen and stuff in here, and you could be like, but Miss West, like, you know, doesn't that overall kind of like make water with carbon? No, the reason why it's called hydrocarbon is because you have hydrogen attached to carbons. Hydrocarbon. Okay, so organic compounds are generally insoluble in water and soluble in non-aqueous solvents. So what I mean by that is, like if you think about butter or oil, oil does not mix with water. They are not soluble in each other. So going back to my butter picture, this would not mix well with water, and the reason why it wouldn't mix well with water goes all the way back to our intermolecular forces unit, where we know that like dissolves like. I know not everyone likes that saying, but the key thing is, like, polar molecules like water are attracted to other polar things, like salts, where you have, you know, sodium is the positive charge and chlorine is the negative charge. You don't have that with organic compounds. This is, I know it's not perfectly symmetrical, but this is a largely non-polar molecule. So because it's non-polar and water is polar, they don't like each other. They gotta be the same, like, type. They gotta be polar likes polar and non-polar likes non-polar. If you think about it in terms of people, you know, like, you might say, like, kind of like crazy people and like really chill people like other really chill people. I know that's not always the case, but that's kind of like my analogy at the moment. So, organic compounds, they don't mix well with water because they're non-polar and water is polar. Organic compounds are non-polar. The exception is some organic acids, such as acetic acid. They are somewhat soluble in water. Organic compounds are generally non-electrolytes. So going back to what the term electrolyte means, an electrolyte is a salt. So it's all our ionic compounds, like sodium chloride, sodium fluoride. Those are our salts, and they're not salts. Organic compounds like butter, you know, you could have salt in it for sure. At the grocery store, actually, there's the option of getting butter that's salted or not salted. So you can have butter without salt. So that's all that's saying. Organic compounds are generally not electrolytes. So when dissolved in solutions, organic compounds do not form ions. So basically, if we go back to our butter for a second, when I look at this compound, if I had a salt and I put the salt in water, like sodium chloride, we know that the sodium separates into sodium ions and the chlorine will separate into chloride ions. This is not going to separate. It's going to stay together as one blob of a molecule. It's a big molecule. So because nothing comes off of it and nothing goes onto it, it stays as a molecule that's neutral in solution. It is not considered to be a salt or an ionic compound. It doesn't separate. Okay. So they do not conduct electricity because, again, they do not separate into ions. You really need charges for electricity to happen. Characteristics of organic compounds. So organic compounds generally have low melting points. Again, if you think about a tree, you'd be like, but Miss West, like, my tree in my backyard, it's not melting. Well, hopefully it's not melting. I would be like, yes, okay, you're right. But when we're thinking about organic chemistry, the best compound to think about is butter. I know not all carbon things, like, we don't melt easily, or hopefully at all. I have never really thought about that. But yeah, just think about butter, because butter is generally a lot of organic compounds have the properties that are similar to butter. So butter melts easily. It has a low melting point because everything kind of goes back to intermolecular forces. There are nonpolar molecules, so they don't have a strong attraction for each other. So they melt easily. Organic compound reactions. Most reactions involving organic compounds are generally slower than those involving inorganic compounds. We're actually not going to talk a whole bunch about organic reactions because of time this year. Yeah, but I guess that's an extra fun fact. Okay. What about bonding? So, in your textbook, you should have written notes on this, that the carbon atom, it has 4 valence electrons and can therefore form 4 covalent bonds. So if you go back to your reference table and you go all the way down and you're looking at carbon, let me just rotate this real quick. So carbon has 4 valence electrons. I know it has overall 6 electrons, 2 plus 4 makes 6, but it has 2 in the inner orbital and 4 in the outer valence orbital. And we care about valence electrons because valence electrons are the ones involved in bonding. So carbon has 4 valence electrons, and you could write its Lewis dot structure, which I will do, to be, here's our carbon, we just put 4 little electrons around it. Again, the magical number in chemistry is 8. So it's going to want to have 4 bonds so that it can ultimately have 8 electrons. Because each bond involves 2 electrons and it can share the 4 it has, and maybe another element can share 2. So this is what the Lewis dot diagram for carbon looks like based on its valence electrons of 4. So it has, it makes 4 covalent bonds because, again, it's trying to get the magical number 8. In terms of its molecular geometry, this is really pushing us way back, but it likes to form a tetrahedron shape, otherwise known as tetrahedral. I know it's been a while since we've talked about that, but this is kind of like what it looks like. So you have, you're going to have 4 bonds coming off of carbon, just always. That's just how it is. And that's because it has the 4 valence electrons. Those are really awkwardly placed. My PowerPoint got a little wompy. This is the electron configuration, and again, the shape is tetrahedral. I'm not going to talk too much about electron configuration because of time, but if you look at the electrons overall, you have 2 in the 1s, 2 in the 2s, and 2 in the 2p. Overall, that makes 6. So we have the right number of electrons here because they add up to 6. And so alright, the carbon atom can share electrons with other carbon atoms. Again, it has 4 and it wants 8. So it likes, the way it gets 8 is by forming bonds with each of its 4 valence electrons. So it does that. And so it can share 1, 2, or 3 pairs of electrons. This is how it likes to bond. You'll always just see 1 carbon with 4 lines coming off of it, and then it bonded usually to another carbon, which also has 4 bonds coming off of it. You can actually also have a carbon double or triple bond. Notice how this carbon right here, it still has 4 lines coming off of it. It has 1, 2, 3, 4, because there's the double bond, there's 2 lines right there. So